So today we start with generalized methods of moments, and the first part is a crash course or refresher of instrumental variables and methods of moments estimation. And I'll start with just very simple notions of instrumental variables estimation. Then I move to methods of moments, the principle, and then its generalization to generalized methods of moments. Let's set the stage by thinking formally about what are the assumptions or conditions, if you wish, that we need in order for the classic ordinary least squares regression to work. And just to set the stage, this is a linear relationship. Those of you who were here last week already know this. Most of the notation will be in the matrix notation. So to set the stage, we have a vector of observations on the dependent variable y. We have an n by k matrix of observations on the explanatory variables, a matching vector, that's a column vector, of k by 1 of the coefficients in the model, and then a vector of error terms. And so basically what ordinary least squares is about is, or classic regression is about, is what are the conditions under which we get these great properties for least squares, specifically unbiasedness, which is a finite sample property, meaning that on average the estimator is on target, as well as consistency, which is a large sample property, which means that in the limit, in this conceptual abstraction of an infinitely large data set, the estimator is right on target. And the formal framework to accomplish this is a textbook Gauss-Markov theorem. We won't go into that, but what I do want to do is to step back and think about what are the various conditions that we need to get there. And the reason I do this is I want to start with something that is hopefully somewhat familiar to most of you or all of you, and then move into more and more unfamiliar terrain, and you will recognize it's always the same thing, but it's put into slightly more complex form to allow these more complex models. So I won't list them all, but just to set the stage, typically one assumes that the X matrix of observables on the covariates is not stochastic, but it doesn't have to be. So the textbook case, classic textbook case, is X is fixed, or fixed in repeated experiments, but it doesn't have to be. And in modern econometrics, it's not at all. All you need is some limits on the variability of the X. And typically, this is obtained with finite second moments. So that means you cannot have infinitely large observations. Basically, that's what it means. Secondly, the error terms. Typically, the error terms are IID, independent, very important, because we'll deal with spatial correlation, which is not satisfied, does not satisfy independence. Identical, as we'll see shortly, most spatial models yield error terms that are not identically distributed in the sense that they're heteroscedastic, so their variances are not constant, therefore they're not identical. Or in the more modern literature and the more modern textbooks, this non-identical distribution, specifically the heteroscedasticity, is acknowledged up front and so taken into account. Thirdly, and very importantly in this context, is that the explanatory variables X and the error term are uncorrelated. And basically what this means is that there is a separation between the information content of the model, which is in the X, and the rest, the noise. And the noise should not be correlated with the information content of the model. That's the bottom line. So the way this is set up formally, and this may not be familiar to you, but it will be very important later on, is that conditional on the error term, this is actually the other way around, there is no correlation between this is the other way around. So the conditional expectation of the error term given X is 0, and that implies that the expectation of the error term is 0, or that the correlation between the covariates and the error term is 0. Now, these are all different ways of saying the same thing, and they're actually a little weaker. They're not as restrictive as this conditional expectation is to begin. And the difference here is pretty subtle, but it has to do with the difference between finite sample properties and asymptotic properties. And basically, we will not deal with finite sample properties. We'll move to the limit because all these models include spatial autocorrelation, and there is no way you can deal with that in a finite sample context. So for our purposes, what really matters is this property in the limit. And this is very abstract in some sense. It's the probability limit of something that looks like an average because it's 1 over n. So it divides by the size of the sample. It's an averaging kind of operator, an averaging of, if you wish, the cross products of the observable covariates and the unobservable error terms. So for a conceptual, very large data set, that average has to converge to 0. So in the limit, and this is purely a construct. This isn't real. This is math. So we need these properties in order to establish that our estimators actually work. But how they work in finite samples, in most cases, we don't really know. And we'll talk about that more as we go on. But in the limit, we need to have that these two are not connected together. Okay, what happens when this is not the case? When we have correlation between the explanatory variables, the covariates, and the error term. And when would this happen? This would happen, for example, if some of the variables are simultaneously determined with the error terms. An example that you may be familiar with is a time lag in the dependent variable. So you have yt minus 1 on the right-hand side, and the error terms are also serially correlated. Then the two, because they both go back one period in time, they both are jointly determined, so there is no longer this uncorrelatedness between the covariates and the error term. Another case, which those of you who were here last week should know, is when we have a spatially lagged dependent variable on the right-hand side, then again, that is correlated, jointly determined with the error term, so there again we have a problem of simultaneity. There are two ways to consider this. One is finite sample, one is large sample. Finite sample deals with the expected value. Large sample deals again with this probability limit. And what we see is that the OLS estimator is biased and also inconsistent. So both the finite sample property as well as the large sample property are not satisfied when we have this correlation. And just to set the stage for later, and I apologize ahead of time because the notation gets quite formidable. These are basically half slides full with one equation on them. But the logic is very simple, because what we're doing here is we're putting down the OLS estimator, x prime x inverse, x prime, and this is y. This is the population expression for y. So this is the true value of the parameter and the true unknown and unobserved error term. So then we work this out, and these two cancel, so we have the true parameter value, and then we have this other thing. And this other thing is what we will be focusing on also later on in order to get the actual properties of the estimator. And in this particular case, we see that since the expected value of x prime u is not 0, this second part is not going to be 0. Therefore, there is a difference in a finite sample setup of the expected value of the ordinary least squares estimator and its true parameter value. So that's the finite sample case. Then we have the large sample case, where instead of using the expected value, we use this plim, the probability limit. What is this, since this is a random variable, what does it move to on average, because we're dividing by n? And so it should go to 0. If it doesn't go to 0, we can follow the same logic here. We have this part and that part. So the first part, as before, cancels out and gives us the true value of the parameter. And the second part gives us the plim operator applied to each of the parts of the product separately. And so you see, this is where what we call regularity conditions come into play. These are basically assumptions that make sure that everything works right. So the first regularity condition will have to do with this probability limit, x prime x over n, and we'll have to guarantee that this actually exists. So if it converges to some fixed matrix, we're fine. There's no randomness in that part. That's the important aspect. All the randomness is in the second part. So if the second part, under this assumption again, does not converge to 0, then again we have a non-zero part that is added to the true value of the parameter. But now this is in the limit. This is asymptotically. So asymptotically we are off. The estimator does not go to the true value of beta, but it goes to beta plus something. Okay? And that's the main problem. This is... Did you have a question, Paul? By the way, if you have any questions or anything that comes up, feel free to interrupt. I actually like that. It gives me a break from doing these slides. So here the instruments come into play. And we reformulate the model slightly, again, to be following most of the notation in most of the textbooks. And we have a matrix of covariates or explanatory variables z and a matching vector of parameters theta. The rest is the same. But now some of the z are correlated with the error terms. So we actually have in explaining why, we have two sources of variability. Remember, previously the x was not really a source of variability because for all practical purposes we could treat it as not being random. But now that's no longer the case. So we have both variability from the z and variability from the error term. And in comes this instrument, which is a new variable. A new variable where now, this, at least here I wrote it correctly, the conditional expectation of the error term given the instrument is 0. So this is something that comes out of nowhere and has the proper lack of correlation with the error term. And in order to be useful, it also needs to have some correlation with the original variable z. So in principle then, we are going to try to solve this problem of the inconsistency by bringing in a new set of variables, which we call instrumental variables, that satisfy the uncorrelatedness with the error term and are somehow correlated with the original variable. Okay. Now the tricky part in practice will be what should these instrumental variables be, and we'll talk about that some more later on. But the principle is simple. We have a problem. Some of our z's are correlated with the error term. We'll fix the problem by getting some new variables that are not correlated with the error term, but are correlated with the original variables. And in some sense, and I say this very loosely, in some sense, these instruments will replace the original variables in the estimation process. And for that to work, we have to have certain conditions. And I put the classic textbook conditions here in front of you, and I want to put them into perspective so you see what exactly this means. And in fact, they're all very practical. They may not seem that way if you look at them the first time in a textbook, but they're actually common sense. So we have a matrix, which I've called here, tried to be consistent, I think there's only 1 or 2 slides where I'm not consistent in the notation. But I try to call it Q. Now, I'm saying this half seriously because the textbooks are not consistent at all. In some textbooks, the instruments are Z, sometimes they're H, sometimes they're Q. And so you really have to pay attention when you read this stuff. It's very confusing in the beginning. So let's just stick with Q. And Q is the same dimension as Z. This is very important. So there's a 1-to-1 correspondence, if you wish. It actually doesn't quite work that way, but you can think of it that way, as a 1-to-1 correspondence between an instrument and an original variable. Now, some of the original variables may be instruments for themselves. If in fact they are not correlated with the error term, if they are so-called exogenous, they don't need an instrument. So you just put them in the Q matrix in place of themselves. First of all, we don't want multicollinearity introduced in the instrument matrix. So formally this means, and remember all this stuff is in the limit. So formally this means that the probability, you'll see this part each time, this just means we're going to the limit. We're thinking conceptually of a very large data set. This 1 over n means there's some averaging, because these are huge matrices. These are, Q is n by k. K doesn't change. K is the number of variables, but n changes. So as n goes to the limit, this becomes a longer and longer matrix. And so in order to keep things comparable, that's really the reason behind this. This is divided by the number of observations. So everything is kind of rescaled back to some notion of an average. It's very similar to the notion of an average. So this matrix, you can think of it as Q primes Q, Q transpose Q, has to exist, has to be finite, has to be positive definite. In other words, don't use 2 instruments that are identical. Each instrument has to contribute something separate to the game. Okay? That's what lack of multicollinearity means. Secondly, as we said informally previously, these instruments have to be somewhat related to the original variables. And the way we formally express this is that this matrix Q prime Z, Z being the original covariates, and Q being the instruments, has to be finite and have a proper rank. And the rank is, again, some measure, some indication that we have independent pieces of information. Okay, that if the rank was less, then it would mean that there is some interdependency there already that is superfluous, that is too much. So we want to make sure that there is some. We also want to make sure this is not 0. So that's the rank is one thing, the finite is another thing. We want to make sure this is non-zero. If it's 0, that would mean there's no correlation between the instruments and the original variables. That's not something we want. And all these are the theoretical limits, these HQQ and HQZ. In practice, we will actually be using the matrix products Q prime Q and Q prime Z, which you may recognize from textbook examples. In practice, all these n's disappear. They all wash out. So they have to be in here to be theoretically consistent, but in practice, you don't have to worry about them. And I'll point that out a number of times as we go through these expressions. These n's pop up, and then they disappear again. And you might wonder, well, what happened to these n's? Well, you need them theoretically to rescale this possibly infinitely large matrix multiplication, but in practice, they all cancel out at the end of the day. So we have the correlatedness with the Z, and then we have the uncorrelatedness with the errors, namely Q prime U should be 0. There should be no correlation between the instruments and the error term in the limit. So with these pieces in hand, and these, by the way, are assumptions. This is not true automatically. We have to make sure that it is true. So with these things in hand, then we can move. And we have the instrumental variables estimator. And for those of you who might be running ahead a little bit, instrumental variables estimator is in the strict sense. This is not the same as two-stage least squares, and I'll clarify that in a few minutes, but I want to raise a little flag about that ahead of time. Oftentimes, you think of instrumental variables as being two-stage least squares, and in fact, two-stage least squares is a special case of instrumental variables. But the pure case is one where Q and Z have the same dimension, have the same number of columns. So the pure case is the 1-for-1 case. One instrument for one variable. The instrumental variable then formally is Q prime Z. Q is the instruments, Z is the original matrix of covariates. This inverted Q prime Y. Why does this work? Well, let's put in the original Y as it's in its full expression, and then we play the same game as we did before. We just multiply this out. So we get Q prime Z inverse times Q prime Z. That cancels, and we end up with theta. So we have the first part of the picture. We are converging to something that makes sense. The second part is the remainder. So it's Q prime Z inverse Q prime with the error term. And this, we have to now make sure that this somehow disappears as we move to the limit. And then we have consistency. So the estimator, the good part is that there should only be one equal sign. It equals theta and then something. And the something has to go to 0. How does the something go to 0? If we can ensure that the first part is somehow fixed, then all we have to do is deal with the second part. And the source of randomness comes solely from the second part. And that's the trick. And of course, we've made our life easier by assuming these things. In the previous slide, if I go back, here's our Q prime Z, that in the limit goes to some fixed matrix that is finite, is not 0, has full rank. And here is our Q prime U, which we've assumed in the limit to go to 0. So then, if we plug these in after we go to the limit on both sides, we have one part, just like in the OLS case, that goes to a fixed matrix, and another part that goes to 0, because we've assumed it to do so. So then, because of that, in the limit, we have our estimate, we have the true parameter value, and we have 0. So the remainder, the difference between the true parameter value and the estimate, goes to 0 in the limit, which, in other words, means that the estimator is consistent. That's the definition of consistency. Okay. So what have we done? We had a problem. The problem was that there was correlation between the covariates and the error term. You can think of this signal and noise, and the signal should not be correlated with the noise. So the way we fix the problem is we come up with new variables, which we call instruments, that don't have this problem. They are not correlated with the error term. So we introduce them, we put some structure in it, in that we make sure that these instruments are correlated with the original variables, and that we maintain that they're uncorrelated with the error term. Now, these are all assumptions. We don't know whether this is true or not. That's where specification testing comes into play. Because we'll assume this and then move forward as if it is true, but then we need to check whether in fact this is valid in the data that we work with. So we know that the estimator is consistent. In asymptotics, there are two important properties, and consistency is just one of them. The second one has to do with carrying out statistical inference, is testing hypothesis tests about the value of the parameter. And I put this in here because It may have been some time since you went through your econometrics textbooks, and this I've always found very counterintuitive. And so I want to stress how this works. It's just a trick. Basically, if you have a consistent estimator, you can't do any inference. Because what that means is that in the limit, you are at the constant value of the parameter. In classical statistics, we're not Bayesian here, not yet, not till Thursday, but in classical statistics, that's a constant. A constant doesn't have a distribution. So if you want to do a t-test, t-test is a difference between the estimator and some hypothesis, say 0, divided by the standard error, which is the square root of the variance. Variance 0, you can't do it. Okay. So for practical purposes, this isn't useful. So what is the trick? The trick is to come up with something that is called a limiting distribution. And a limiting distribution is something that we get by rescaling the estimator. The reason why we end up right on target is because this 1 over n, this averaging for very large numbers, gets us to the 0 for the correlation between the q and the u. Okay. So what we're doing now is actually blowing up the estimator. And we're multiplying, if you think back, let me show back this slide here. So we're focusing on the estimator and then the true value. So if we look at the difference between these two, in the limit, as we show here, the difference between theta IV and the true theta goes to 0. Now what we're trying to do is make the difference between these two a meaningful random variable. And ideally, as is the case, a normally distributed random variable. And that is what central limit theorems are about, is to show how something becomes a normally distributed random variable. So rather than taking the difference between theta IV and theta, which as we know is 0 in the limit, we multiply it by the square root of n. And you might have heard the term root n consistency. That's where this is related to. Okay. We have the q prime z divided by n, and we have the q prime u divided by n originally, but we're multiplying both sides by the square root of n. So this here, the first time you see this, you wonder, where does this come from? That's where it comes from. It's this rescaling gives you the square root of n here. We're interested in what is the distribution of this thing. What is the distribution of the square root of n times the difference between the estimator and the true value of the parameter. And the distribution is completely determined by what is on the right-hand side here. Now, by assumption, this first part is fixed in the limit. We've set it up that way. We've set it up that the probability limit of that cross product goes to this HQZ. So we don't have to worry about that part, at least for now. We do have to worry about the second part. And we do have to prove, we won't do any proofs in here, but that's what is needed, is that this part, this QU divided by the square root of n, somehow goes to a normal distribution with mean 0, so that on average this difference goes away, and with a variance. And this variance, very generally put, and this will allow us to move to specific cases, is the probability limit of, again, some kind of average, of the cross product of q prime u prime q. Now, this part in the middle here, we're used to assuming this to be uncorrelated. So then this is simply sigma squared I, and we don't have to worry about that part. Of course, we're interested in spatial autocorrelation and heteroscedasticity, So this will not disappear in general. And in general, we have this matrix omega there in the middle. So what we will need to do, and we won't do it, there's luckily theoretical econometricians who love doing this stuff, we need to come up with the right kind of conditions under which we can show that our estimator, namely this expression here, and specifically the second part of it, goes to a normal distribution with mean zero and a given variance, specified variance m. Then we're in business, because then we can act again as if theta IV is a random variable. Because then we flip everything around and we say, we go back to the original. So then we say, if the difference between these two is normal with mean zero and variance m, what is theta IV by itself? And forget about the square root of n for a second. That will be normal with the mean of theta. What will be the variance of this? The variance will be the same variance as the difference, but then taken into account the fact that we're rescaling it by the square root of n. And so that's where the n pops in. So, stepping back, we look at the limiting. There's a difference between the limiting distribution and the asymptotic distribution. That's another thing that is sometimes glossed over in textbooks. The limiting distribution is what you get for the square root of the difference between the estimator and the true value. The asymptotic distribution is what you use in a so-called asymptotic t-test. In fact, in an asymptotic t-test, you act as if your estimate is a random variable with a given distribution. That given distribution is this normal one that we just talked about. And we need to find its actual variance, because the variance that we have, this m, is the variance for the square root of n times the difference. So working with this, actually, I should correct myself, the variance is only for this part. Okay? So now we use the rules for variance. The variance of a random variable pre-multiplied with something else, if it's a scalar, is the square of that times the variance of the random variable. Okay? When it's matrices, you have to do the matrix multiplication. So if it's A times U, then the variance is A times the variance of U times A prime. In this case, A is this nice matrix here of Q prime Z. And this is where it gets a little complex in terms of notation. So if we know that the variance of Q prime U divided by the square root of n is m. So then the variance of that pre-multiplied with Q prime Z is the A that I just mentioned, the variance of the random variable, and then the transpose. Okay. Or in the limit, replaced by their limiting expressions. So then, in practice, we can work as if theta IV has a mean of theta, and the variance, that's one more thing that we need to multiply by. It's square root of n, so we need to divide by square root of n to get rid of that, and that gets squared in the variance term. That's where this 1 over n comes from. So we end up with this class textbook expression, which is starting to be unwieldy, but it actually has only two parts that we focus on, two parts that are important. This middle part here, the q prime omega q over n, that's the part that corresponds to this m thing. That's the part that corresponds to the randomness in the error term. So if we have spatial autocorrelation, this omega will incorporate the spatial autocorrelation. If we only have heteroscedasticity, this omega will incorporate the heteroscedasticity. The rest is nothing but a rescaling using the standard rules of computing the variance of a random variable multiplied by a constant. in matrix form. So the variance of a random variable multiplied by a constant is the square of that constant times the variance of the random variable. And here the square is replaced by all these products, the matrix and then its transpose. So those are the pieces. Now the next step is to operationalize it. We're still working in the limit here. This is a limit, this is a limit, this is a limit. And then to make it practical, we replace it by their sample expressions. So we plug these in and we just, instead of using these things with 1 over n, they all cancel out, and so we just do straight the multiplication of the matrices. Everything, the n's are in there to ensure that we have finite values in the limit, but in practice, they all cancel out, so you don't really have to keep them in there in an actual sample data set. Now two-stage least squares. So far, we've had a situation, remember, 1 for 1. One instrument for one variable that needed an instrument. Now what if we have more instruments than variables, which is the classic case? Which ones do we pick? And if we have more instruments than variables, this condition, this uncorrelatedness, holds for multiple variables. So what do we actually stick in this queue? And we can stick any linear combination of instruments in the queue. So think of Q as still having the same number of columns as Z, so it's still 1 for 1, but it's no longer one unique instrument for a unique variable, but some combination of instruments for a unique variable. Okay. So we're going from a strict 1 for 1 to a situation where we have multiples, and we can either pick one of these, say we have 5 instruments and we only need 1. Okay, what we could do is pick one of the 5 and we're in business. But we can also pick any linear combination of these 5, because since they are individually uncorrelated with the error term, any linear combination of them will also be uncorrelated with the error term. And then the question is, which linear combination? And that's where the two-stage least squares come in, because it takes that linear combination that is as close as possible to Z. And this is called a projection. You can think of, if you can think that way in multi-dimensional space, you try to get the plane that is the closest possible to the original hyperplane, if you wish. And this is nothing but an extra regression. This Q prime Q inverse Q prime Z, you can think of as Z as being the dependent variable and Q being the explanatory variables. So for every column in Z, this is a regression coefficient, which is then multiplied again with the original Q to give you a predicted value for the Z. So in other words, you take every variable and you regress it on all the instruments, in our case all 5 of them, and you get the best fit, which is the predicted value from a least squares regression. And then that becomes your instrument. So formally, this is nothing but a specific linear combination of the original instruments, but it is one that fits the original covariates the best. And so if you use a variable as an instrument for itself, then the predicted value is perfect, because your regression coefficient will be 1. So this is a lot of algebra for nothing, basically, because you're just still replacing the variable by itself. This only matters for those z's that are, in fact, endogenous. Okay. And so for those, the endogenous variable, you can think of this as the endogenous variable being regressed on all the instruments and taking the predicted value from that as an instrument for that endogenous variable. And that is then two-stage least squares. And the way this the reason it's called two-stage least squares is you can think of this extra regression as a first stage. So you regress the endogenous variables on the instruments and you get the predicted values. Then in the second stage, you do another regression, but now using these predicted values, the instruments. So if you look at the second stage, you are using the same notation as before. Now Q has become ZP, the predicted values of the Z. So we have P prime Z invert ZP prime Y, but with some algebra, and if you don't believe me, you can do it over the break and check it out. This is all the same whether you use ZP or Z, so you can, in fact, run this as if it was a standard ordinary least squares regression of Y on ZP. And some software packages do it that way. So they first get the predicted values, and then in the second stage run another least squares regression. That's fine, except that the residuals are not the right residuals. The residuals of the true residuals of the model are the difference between Y and Z times theta, not the difference between Y and ZP times theta. So this is something that if you, by hand, if you wish, run this. So first you run your first stage least squares regression, and then you run your second stage least squares regression. If you do your inference, your t-tests, you cannot use the standard OLS residuals from that second stage regression. In fact, you have to make sure that the residuals are in fact these residuals. So not ZP, but Z should be multiplied with the parameters. And then you're in business. You know, you have your residual sum of squares. You can use that as an estimate for the residual variance, and so on. You can proceed that way. And then our nice two-stage least squares expression is this kind of monster, which just does everything in one shot. So you don't actually have to do it in two stages. You just replace the instrument by its expression here in the previous slide. So this is the instrument, Q times Q prime Q invert Q prime Z. So then in the expression, instrument prime Z, we have this whole thing transposed times Z, and that becomes this whole thing here. And then we have the same thing again times the Y. And this allows you then to just run the whole thing in one shot. So two-stage least squares estimation is a special case of instrumental variables where the instruments are taking as, if you wish, the best linear combination of any candidate number of instruments that you might have. And that gets you around this kind of artificial one-for-one choice where you would have to pick one instrument for a particular variable. The asymptotics are the same as before. We just use the general properties that we have obtained for instrumental variables. We stick in the appropriate expressions for the instruments, which are now these very long matrix multiplications, and then you get these kind of nice monsters. The two-stage least squares estimates are consistent. This is their asymptotic variance. They are not the most efficient, meaning that there are other estimators that can get you smaller variance in the limit, maximum likelihood being one of them. And the good thing about them is that you haven't heard me say once, I assume normal distribution. You don't need it. Why don't you need it? Because you get it. You get it through the central limit theorem. I've not gone into much technical detail about it, but the key was to show that this q prime u divided by the square root of n had a limiting normal distribution. That is where the normality comes from that you use in your asymptotic t-test. And you get it from the central limit theorem, which shows you under given conditions and restrictions that you do indeed obtain normality for that expression without having to assume normality for the u, for the error term. So in some sense, it's better than maximum likelihood where we had to assume a lot of structure. And everything is fine as long as that structure is in fact correct. When that structure is not correct, then we have misspecification problems and specification errors and so on. So in a nutshell, what we have so far is that the problem is one of simultaneity or endogeneity. Some of our explanatory variables are correlated with the error term. We fix that problem by coming up with instruments that are not correlated with the error term and are correlated with the original variable. And then we can show that given the right assumptions having to do with how these instruments are correlated with each other, q prime q, how they are correlated with the original variables, q prime z, and how they are uncorrelated with the error term, q prime u, given those assumptions, we end up with an estimator that's consistent, which is good, and also in the limit has a normal distribution, which we can then use to carry out inference in actual real-life finite samples. This is a very subtle but very important distinction, in that the consistency of the estimator gives us something in the limit that is not useful for inference because it's a constant. To make it useful, we rescale the difference between the estimator and the true value, and that, in fact, is then a normally distributed random variable. And once we have that, because of the properties of the normal distribution, we can find out what is the asymptotic distribution of the estimator by itself. See, we start with square root of n times the estimator minus its true value. That is normal with a mean of 0 and a given variance. So then the estimator itself is normal with a mean of the true value of the parameter and a variance that's rescaled to get rid of the square root of n. And that is the actual expression that we use in asymptotic t-tests. So then we saw that two-stage least squares is nothing but a special case of instrumental variables. Special in the sense that we have, if you wish, too many instruments, and we have to pick instruments because it still remains a one-to-one situation, and we pick the best linear combination of the instruments, which is in fact a projection or a least squares regression of the instruments on the endogenous variables. Okay, so that is kind of the basics. Now, after the break, we'll move on to methods of moments and then the generalization, general methods of moments. And just to run ahead so that you know what to look for, as it turns out, instrumental variables will be a special case of a methods of moments estimator, and its generalization will allow us to deal with more complex variance matrices, which is what we want. In the end, we want to use this to estimate models with spatial autocorrelation. That's the ultimate goal.